Okay, so we'll start today's session. So hi everyone. So I will share my screen now. So today we'll see the different methods of design of reinforced concrete structures. Do you guys know any different methods? Have you heard that? What are the different method used to design the reinforced concrete structures? Like anybody knows? Like is the way of designing. So there may be n number of ways you can design the structure. So from that we have some famous methods, uh, 3 or 4 famous methods, and from that currently we use one in all our structures, but in the previous days we were using the different type of methods. So I will introduce that to you guys. So there are 4 different methods: working stress method, load factor method, strength and serviceability method, and limit state method. We can say that it is a if it is going in this way, like from working stress method to limit state method, it is getting improved, and it is getting uh, the amount of material used, uh, like utilization of the material is more good in the limit state method when we compare it with the working stress method. So we'll see that first the working stress method, and then other methods, and then we'll go to limit state method. So working state method evolved around the 1900s. Then it's based on modular ratio, the ratio between modulus of elasticity of steel and concrete. So can anyone tell me what is the approximate ratio between them two, like modular ratio? Like if you consider the elasticity of steel and elasticity of concrete, what ratio you will get roughly, which is also called as m, small m, not big M. No, nobody knows. (280 by 3 sigma CBC). Yeah, it's correct. So we'll see that how it is coming, and what is the significance of that. So let's consider this is the beam with the distance between two support is L, and it is applied by load of P in the middle of section. So yesterday from the last class we know that the bending moment at the center of the span will be PL by 4. So by consider that as a bending moment PL by 4, as we know that this is the formula, very famous formula, this M by I is equal to E by I is equal to F by Y, right? So from that we can calculate M we can say that is equal to F by IY. Okay, so I what is I? Anybody knows what is I and what is the significance of I? Here it is written as a BD cube by 12. So what is that? Anybody knows? And what will happen if the I is more and I is less, and like that? Anybody want to try? What will be the reason? Okay, I will explain you in the short that this I is called as the second moment of area. So it's like if your I is high, which means that it's having the more strength. Like considered as if you're having a beam of width here is a B and depth is D. So consider that if your D is very high, Like consider this section and the similar section with the higher depth. Okay, so the BD cube by 12 will increase for that because depth is higher in the second example. So in that way you can consider that if you load this section with this same load on to these two beams, the first one, which is having a lower depth, will deflect more compared to the second one, which is having a higher depth, which means that the depth of the section with the higher depth has having higher strength. Like if it is second moment of area is high, which means it can take more load. In that sense you can understand that. And y is the distance between the central axis, it is called as d by 2. By solving this we get that m is equal to 0.167 fbd square. So that is explained by professor also in these slides. For the more detail you can watch that video, and if you anyone have doubt you can ask me right away. Sigma is called as a permissible stresses. M is a bending moment, I second moment of inertia. Okay, shall we go ahead then? Yeah. Yeah, so this is calculated. M is equal to 0.161 f bd square. This will be useful in the limit state also. Like this is such a formula you have to remember for the design. Like, so make sure that you remember this. So the next, yes, anyone have any doubt? So
This PPT is not visible.
PPT is not visible.
No, it's full white screen.
Yes, sir.
Okay. Now it is visible.
Yes, sir.
Yes.
It is visible.
So you have skipped this portion. You don't know, and nothing was visible from the starting. This thing.
No, sir.
Okay. Shall I repeat then?
Yes, sir.
Yeah. Okay. So we were talking about the working stress method, which is evolved in around 1900s. So where it's mainly based on modular ratios, the ratios between modulus of elasticity of steel and copper. Okay. So consider this the example where the depth of section is d, width of section is b. Okay, and the permissible stress is sigma, and then this is the beam where the length of beam is L, and it is loaded with the central load P. So by calculating the bending moment at a center location, it will come PL by 4, as it is also calculated here. So as we know, the formula of formula is this: is m by I is equal to f by y is equal to sigma by y, right? So this m is equal to f into I by y by rearranging the formula. And I section I already explained, that is a signifies stress strength of the section, so which is BD cube by 12. So BD cube by 12 is only for the rectangular section. So what will happen if it is square? For the square it will have different formula, and for circular section is also having different formula, pi d raised to 4 divided by 64 and all that. Every section have different I section formula. So by that we calculated the m is equal to 0.167 f bd square. Okay, this type of formula is useful to calculate m directly in a shorter time. So and design the sections, right? So let's consider that in a question it is mentioned that depth to width to depth ratio is 2. So you can directly put into this, and if and more like m is also given, you can directly calculate f in that way. Let's say if f is also given, m is also given, and a ratio of b into d is also given, so you can calculate b and d very easily if you know this formula. So this is by working stress method. So working stress method is very conservative type of design where we uh, where we select the very high factor of safety. Like for considering for concrete, we consider higher factor of safety of 3, which means that we consider the like if like 100 load is coming on the concrete, we'll only consider divided by 3. So that conservative is the working stress method. So the design given by working stress method is always safe. Then why we are not doing our design by working stress method? Can anyone explain? As I said, it is very safe to do the design by working stress method, but then why we are not doing it? Where we generally use the working stress method nowadays? Let's consider that also. Anyone? Okay, so the working stress method we generally not use nowadays for the structures where we know the loads and the type of loads and the maximum allowed load coming on that structures. For example, residential buildings where we know that this type of loading condition will be there. For example, let's say the load of furniture in any flat, or let's consider the live load where maximum how much people can stay in one flat, and the dead load, which is the load of the structure, which is the higher than the other type of loads. And this all things are we know these days. And if we design this structure by working stress method, which will consume lot of material, anyway it will be safe structure, very safe structure compared to limit stress method and other type of methods for designing the structures, but it will consume lot of material. So by that way it will be not economical to construct the structure by working stress method. But yes, but the structure which is very important and is very critical for, and where it's like very critical structures where we want very high safety, there we can go for the working stress method. For example, let's say the construction of dam. So dam construction can be done by working stress method. Why working stress method should be adapted? Yeah. Krupesh have given the answer that is used for dams and bridges. Yeah, you guys can talk also. Like I'm not able to see this screen, so that's why. Okay, maybe I will take this to the next screen so I can see you guys. What are you typing? Okay. Okay. So yes. So why dams we use working stress method? Because it's very critical structure. If somehow the extra loads are coming on the structure, for example landslide into the back uh, like uh, where all the water is stored, catchment area, if there is a landslide happening, which will exert a very high pressure onto the wall of a dam. In that case, the factor of safety which is be considered for the limit state method will not be sufficient to withstand the load which is uncertain coming on the onto the structure. So that's why working stress method will be good and it will resist that loads also. So yes, we'll move forward. Let's say this is the example. Here you can see this is a cross section of beam. What are these? These are the steel bars, and you guys know that there are the limited diameters available into the market as per the IS code also. It's like 8, 10, 12, 16 mm, 16, and then I think 24, 32. In that range we this bar sections are available. So let's say consider you design this section. What is mean by design? Design means defining the depth of section, width of the section, the area of concrete, and the area of steel. Okay, consider you got all these things, like you got the BED and the AST. What is AST? AST is the area of the steel. Then how will you provide the number of bars? Can anyone tell? How will you provide the number of bars? Let's say you got the area as a 100 mm square or centimeter square, and you want to give the number of bars. Now how will you give? By simple mathematics. You know the one area of a bar, so you will divide that by total area, whatever the AST you got from the design, and you will give the number of bars. Now there is a catch. Now some person from, let's say in this class, someone can select the diameter which is, let's say, only 10 mm. Someone can select 16 mm. Someone can select 12 mm. So the number of bar for each person may vary, which does not mean that the design is wrong or correct. Every design is correct only. It is just a convenience of that designer to provide such type of detailings. So by there is also one more code which also provide the guidelines for the selection of the steel bars, where it will be easy to implement this into the sites also. Let's say if someone is designing everything by just 10 mm bars, so it should not be good, no. So every section will have very small bars and lot of bars. So at the site it will be very difficult to handle, like bend the bars and all these things. So there are some guidelines, like for the columns 12 mm bar is the minimum, I guess, and for the slabs 8 mm is the minimum. But as a secondary bar, but primary bar, I think it's 10 mm. You can check this into the IS 456, which will give the more details on that. So assumption, what are the assumption in this thing? So both steel and concrete acts together, perfectly elastic at all stages of loading. What is the perfectly elastic? Which means that structure is not deforming and it is under the elastic limit. Okay, everyone knows the elastic limit of the steel and concrete. Like yield point and the elastic limit. Everyone knows. You can raise hand up if you know. So factor of safety, as I said, the concrete about 3 with respect to cube strength is considered as the factor of safety for concrete, which is very high, and steel is about 1.8 with respect to yield strength. So this means that we are designing a very conservative method for designing the any structures. So but later on we'll study the limit state method, where this factor of safety is considered as 1.5 for the concrete and 1.1 for the steel, which means that so we are using less concrete and less steel to achieve the same strength. So optimization of the section, as we can say, and use of less material. So major defect is deal only with the elastic behavior of the member, right? If it is above elastic limit, this method will not tell us anything about that. So everything should be below that. So it results in a large percentage of compression steel. Yeah. So what is compression steel? Compression steel, I will tell you. So this is the called as a compression steel. Can you see here the above section? Like in a beam, that this is called as a tension steel, which is at the down section, which will when the beam will deflect, it will go under tension, and the above one is called as compression steel. Can anybody knows that what is the purpose of compression steel, or is it required to even give the compression steel? Anybody?
To resist buckling.
To resist buckling. Okay, anyone else? Consider it is as only simply supported, which will only have a bending moment. Then is it required to provide a compression steel? As we calculate AST, so AST we calculate only considering as a tension steel. Okay, like whatever we calculate, let's say calculate our AST is coming as 100, and we provided two bars of 50 mm square. So that's done. Why this extra 2 we are providing it? Or we have to do 100 divided by 4 and give 4 number of bars, or we have to do like that or not? So we can't do like that. Like if it is your AST is coming as 100 mm square, and if you are dividing it by 4, which means that you are designing your structure with AST as a tension, whatever the tension reinforcement you want, which should be given as a tension reinforcement only, because our design is only based on tension reinforcement. So you can't provide that to the compression reinforcement. So for the compression reinforcement, we'll provide extra bars just to hold these stirrups. Okay, you can see it here, this vertical, right? Can you see this thing? Vertical bars, they are the stirrups. So for the holding of that, we provide a compression steel. Okay, can anyone tell about the difference between this and this, like support conditions? What are the difference between support condition? What is called as this support condition, what is called as this support condition?
It's simply supported and down one is fixed.
Yes, correct. Okay, yeah, because you can see it here, this is a wall and this is a beam, just rest on the wall, so which means that it can move in this direction, so which is the characteristics of simply supported. And here, as you can see, it is or beam and column are fixed. It's called as a fixed beam. Okay, go ahead. Yeah, so this is a different type of mechanism. Can anyone tell? This is the fixed, yeah, obviously, because this is RC column, this is a beam, and this is a brick wall. So this is we can break down this structure into this form where it is fixed at here and it is supported by here, as simply supported, right? And the bending moment diagram of this is given by heat here. So here it is having compression at, like here is tension is always at the top, right, and compression is at the bottom, which means that in every normal beams where our tension reinforcement at the bottom will shift to up, like the vice versa will happen. So the compression seal will become at the lower part, and the tension beam will go tension reinforcement will go to upper part because of cantilever action. So major defects: it is ideal only with the elastic behavior of the member. It is result in a larger percentage of compression steel that we already discussed. Concrete does not have a definite modulus of elasticity. Yeah, because it changes with respect to time also. So on a general note, how we calculate the modulus of elasticity of concrete by this formula: 5000 FCK. Here it is written as 5700. I think in your code it is 5000. Please check that. IS 456 is 5100 FCK. But there is a problem. You can't always use this formula for this for the concrete, which is very stiff and which is very having higher compressive stresses, like a grade of concrete, very high grade of concrete, that there you can't use this formula. So you can consider this as a thumb rule formula which is empirically derived. So the load factor method introduced in 1956 in USA and 1956 in UK. The load factor method: the strength of the RC section at the working load is estimated from the ultimate strength of the section. The load factor is the ratio of the ultimate load section can carry to the working load it has to carry. Okay, so they are the load factor. So that ultimate load they will apply and calculate this strength, and that working stress method load. What are the difference between these loads? That ratio is called as the load factor, ultimate load and working load. Reasons towards ultimate strength design. So why we went for this design? Reinforced concrete section behave inelastically at higher loads. Ultimate strength design allows a more rational selection of the load factors. And the stress strength curve for the concrete is non-linear and it is time dependent. As we said that in the previous working stress method, it is considered as a linear, and which is non-linear and which is also dependent upon time. So that was the reason to selection of this method, but there are also drawbacks that we will see now. So the problem with this is that if we design for the ultimate load, so it's safety concern is the problem. Like there is no factor of safety applied to this in this method. So for the next method, there is a design for the strength and serviceability, as already we discussed in the last class, where the strength, if we design it for the strength criteria only, then also there is a problem of serviceability that also should be considered. Like for the example, what is the serviceability criteria, which means that there should not be a cracking in your structure, there should not be excessive deflection, and that is considered in the serviceability criteria. For example, if you design for the enough strength and your deflection of your structure is high, and people are scared even going to that structures, so which means that it is a safe structure as you design for the some strength, but it is not serviceable. No one want to go there because it's already deflected, and it's not comfortable to stay in that structure. That's why this both criteria should be matched. If the section are designed by the ultimate strength requirement alone, the cracking and deflection at the service load may be excessive. So that was the concern, and it is necessary to keep crack width and deflection within the reasonable limit values. So because of that, the serviceability criteria comes in a picture. Why that is required? Why there should be a necessary to keep a cracks width and deflection within the reasonable limit? Why it is required? Anyone knows why we are going for serviceability check and limiting the crack width and also the deflection into the structure? Like anyone can think of like this, my structure is safe for the load whatever is coming on that structure, I should not worry about the deflection, it's okay. So why not that way, and why we are considering the serviceability criteria? Okay, for example, if your structure is deflecting excessively, it will lead to crack, and if your crack is more than whatever the limit is provided, then this crack can allow a very hazardous material to go inside, which we can further start degradation of the structures and which will lead to a lowering down the service life of your structure. So that's why the serviceability criteria is also required. So limit state method, now we'll study about the limit state method. So limit state method correspond to each of the states in which the structure becomes unfit. Okay, so we should be in each state, like loading and the factor of safety also we have to consider for that, or considered as a limit state, may be classified under two broad categories: serviceability limit state of failure in respect of deflection and cracking, and limit state of failure in respect of strength in a shear, flexure, torsion, bond, and combined effect. So in this, all these criteria that should pass the check, and also with the serviceability, then only it will call as a safe structure in the limit state. As I here you can see, no, it is written that correspond to each of the state in which the structure becomes unfit. So it should be fit into the all this criteria. Okay, in the exam solving the example, we will understand that we are check if we design for the strength also, that then also we will check for the shear, flexure, torsion, everything we have to check. In that check we'll understand that by designing is not enough, you have to check it for the other type of loading also, whether your structure is safe in that type of loading or not. So characteristic strength, so that we already discussed yesterday in the last class, the strength that one can safely assume for the material are called as their characteristic strength. So safely assume means what? Safely assume means that the term characteristic strength means that the value of the strength of the material below which 5% of the test results are expected to fall, which means that if you have 100 cubes and you design your concrete for, let's say, M20 grade, so from that 5 cubes can be lower than 20, so that is okay, but all other 95 cubes should be greater than 20 Newton per mm square, whatever the strength that you assume. Let's say that's one example. You can assume it for any type of thing which should have the 95% probability of success and 5% of failure. So characteristic load, the maximum working load that the structure has to withstand and for the which it is to be designed is called as characteristics load. So different type of loads. What are the different type of loads as we are discussing in the residential building? The dead load, live load, wind load, earthquake load. Okay. So earthquake load is coming due to the earthquakes, wind load is coming due to the winds, live load because of we are staying there in the structures, and dead load is itself the dead weight of the structure. So yeah, so DWESS is dead, wind, earth, and live and load. So partial safety factor for the loads, factor load, characteristic load, and partial factor for the loads, so that we already discussed. So the value of partial safety factor for the load and ultimate ultimate limit state is given here. So for the dead load it is considered as 1.5, live load is considered as 1.5, which means that if dead load, if you calculate, we have to consider 1.5 times of that dead load. Okay, in the combination of dead load and live load only. So it's like it will be 1.5 and 1.5. Like for example, in your question it is given that there is only dead load and live load applied. In the design aspects, you have to consider the load coming on the structure is 1.5 times the dead load given and 1 times the live load given. So for the dead load and wind load it will become 0.9 and 1.5. For the dead load and wind load it's 1.5, 1.5. So it's for the DL contributing to the stability, so it's 0.9. For DL assist overturning, it is 1.5. And the value for the partial factor of safety for the loads, if these all are coming together in that aspect, is not 1.5, it is 1.2, 1.2, 1.2 for all. So have you seen that there is no combination where all four are acting together? Everywhere it is 2 or maybe 3 and 2, maybe everywhere it's 2 only, 2 or 3. Why is that so? Let's say here also dead load, live load, or earthquake load 1.2, 1.2, 1.2. Here also dead load, live load. This was for ultimate limit state. Now this is for limit states of serviceability. In serviceability, these all are given in IS codes 456 2000. 1, 1 and 1 for everything. For live load is 0.8, wind load is 0.8. Again here you can go through all the IS code 456. Okay, so these are the different type of loads we required to calculate the load coming onto the structure to design it. So the first part we are considering it is what type of different loads are coming and what are the different partial factor of safety we have to consider. So that you have to consider it anyway. If you are not considering it, no one will approve your design. Let's say you pass out from your college and you went into the industry and you are saying that I will not use this 1.2, I will use myself something different. Let's say you will use 1.7 and let's say 1.1. No one will listen to you because it is given in IS codes and that is calculated by repeatedly doing lot of experiments and lot of trials. These loads are coming. So IS codes are also developing with the time, and all researchers are trying to develop IS code. So this might change in the future. So if the revised IS code is coming, then you have to consider the revised tables and what are the different norms given in the IS codes. So yeah, so there was one question, why we are not considering these things all together? Dead load, live load, wind load, or dead load, live load and earthquake load. In that combination only we are applying, not all together. Why is that so? Okay, I will tell. Because like there is very less probability where you can observe wind load is coming onto your structures at the same time earthquake is also happening. It's very rare. That's why it's very rare possibility to happen, and that's why it is not considered. And in a general sense, we can say that if this situation arrives, if you design it for the earthquake load and wind load, in that severe situation, nothing like our structures will not be sufficient to withstand that. The very bigger climate is like if the earthquake is very in a high magnitude and all. So that's why we always say we can design the structure which is earthquake resistance. not earthquake proof. Okay, so there is always a limit. Any question till now? So yeah, in this thing, Professor, we are working on this software. You can also try it online to design whatever you want to design. Where he designed the footings. These are the different footings. So, which type of footing this is called as? Can anyone know? Can anyone tell that which type of footing is this? You can type on the chat. This is the isolated type of footing, right? Yes, and then there was he constructed the columns, and then slab, and then tie beams also. What are the tie beams? This is called as a tie beam. See, these two columns are attached together as some height from the footing is called as a tie beam, which is usually rest on the wall. Beneath it will be wall, and then above that will provide a tie beam. Okay, why we are providing tie beam? Anybody knows? So in this live session we'll try to solve the reasoning behind it rather than solving the problems, because that you can do it by just listening to the videos, right? And by seeing the solved example, so you can design any slab, any column, any beam, which is easy. It's not a difficult part. We'll try to find the reasoning behind it. So yes, what will happen if I am not providing tie beam? Let's say these tie beams are not provided. Now what will happen to my structure? Okay, one more hint I will give you. Let's consider the soil beneath this footing is not having enough strength. So what will happen? Anyone? Can anyone tell what will happen if soil is not having enough strength below the footing and we are not provided tie beams? Okay, let me explain about this. See, consider if there is no tie beams provided, so which means that each and every column and footing is independently acting. Okay, so there might be a differential settlement. Let's say this column and the soil beneath it is very weak. It can settle a lot. This can settle a little. So which means that in the structure there will be a differential settlement, and a differential settlement is very, very bad for any structure, because of differential settlement there will be stress generation in your structures, and the torsion might also will come, and cantilever actions will also happen to your beams, and due to that your structures will start showing the cracks, because it was not designed for that phenomena. We have not considered it. The structures will settle, and that's very bad for the structures. So this tie beams, if we provide, and consider from this one column is having lower, the soil below it is having the lower bearing capacity. Even if it is having bare capacity, if some load can be distributed by this tie beam to other footings where there is a high bearing capacity beneath the soil, so which means that this tie beam will restrict the differential settlement of the structures and try to provide a uniform settlement to all the structures. So if any If any structure is uniformly settling, that is not that much problematic compared to differential settlement. For example, if you are, let's say this, if you cut this structure into the half structure is settling down like in this way, and the other structure is at this location only, so which means that this beam and all will try to prevent that settlement, and if this is not there, there will be lot of stresses development into the columns and the slabs also. So that was the reason for providing the tie beams. Okay, so this was the software he used. You can also guys use POV ray. So yes, so direct tension is provided by this PAT IS 4 page number 80 IS 456 2000. So for every grade there is a tensile stresses provided. For M15 is 2, M20 is 2.8, M25 is 3.2, M30 is 3.6. On an average, it is 10% of the compressive stresses, as we have discussed in last class. The tensile stresses, tensile capacity of any concrete is a 10%, about 10% of the compressive strength. Okay, so the permissible stresses in a concrete, here is a grade of concrete. Permissible stresses in a compression bending, here is a direct, and permissible stresses in a bond average for the plain bar in a tension. That is also given in IS 456, as you can see it here. So bending stresses and the direct stresses and the bond stresses are also provided. So this is we required for the design purpose. Okay, because someone is telling no 280 by 3 sigma CBC. So this is CBC, you will take it from here. Let's say in a question it is given as M20 you have to design. So this say 280, it will be 280 only, 3 sigma CBC. So sigma CBC will take it from here. But in example, if it is, they always mention that only direct stresses you have to take, then you have to go for this. Then bond stresses also. So this all are required. So I will suggest that in a free time always go through the IS codes and try to look where which tables is mentioned, where which figure is mentioned. So that is required to get handy with the IS codes, because while in the exam, if someone is asking question, you should be able to directly find out which page number you have to go and which value you have to pick, because you don't have time there to write, no. So that is required, so you get habitual with the code IS 456 for the design purpose. So obviously for the steel it will be very high loads. See here, it's only 5, 7, 8, maximum it is 10 N mm square, Newton per mm square. But in steel it's like 140, 130, 230. So for Fe215 and Fe415. So what are the different grades? What is this 250 and what is this 415? Can anyone tell? Yes.
Characteristic strength, sir.
Yeah. More into that. In a stress strain graph, this 250 and 450 is called as yield strength, right? Okay. So nowadays we don't use Fe215, and we only use mostly is Fe415, which is called as HYSD, right? Here it is written high yield strength deformed bars, HYSD. Okay. So the tension stresses can be calculated by this formula, Ft by AC plus M AST.